So either you have central bearings that you're using, or you put it on a four-wheel setup. It's either knee here and a knee there. Spin it up to see when it starts. On the load cells, so then you can actually time, you get phase information how the up and down on each end works. So it's balancing.
I guess if we were interested in how the aerodynamic forces affect like that.
There's too many variables right now. You can put in one something and get something. It's kind of hard to say.
Teach better?
I think, maybe taking out the one complex
Yeah, I was like, personally, we got people coming before our project really soon now. He's like, you're gonna have to. Also, you know how much it would cost.
That's it. Like.
So because a lot of like you had like
yeah, we also gotta talk to Sardi about our scheduling earlier.
So usually a classic, okay, let's get outside of here because we've got people who actually want to teach here.
Okay, so let's start. So today we're gonna look at the last characterization of expander, which is to view it in the probabilistic way. And the message of this class is to say that expander are exactly the graph such that random walks mix rapidly. So I will just need to tell you what are random walks and what it means to be mixed. Okay, and so random walk is just a very natural process where suppose that you have a graph G, you're given a graph G, and let's say for today's class, the degree profile of the graph is D. And then, so we said that to do a random walk step on the graph G is just a very simple process where suppose that you are now at a vertex U, then what you do is you just choose a random neighbor of U, say V, and move to that random neighbor. So it's very simple process. You are now at U, and if there are like 4 neighbors, then just choose one of them randomly, uniformly. And let's say you go this one. So each of them will be chosen with probability 1/4 here. Right. So you go to V, and then that's your random walk step. Very simple. Now if the graph is weighted, then we can define it just analogously. It's just that if you are at U, you just choose your neighbor V, proportion such that the probability is proportional to the weight of the edge. So if this is U and this is V and this is V1, V2, and if this is let's say the weight is 1 and 9, then you go to V1 with probability 1/10 and here with probability 9/10. Okay, so that is the random walk step, and basically we would like to understand what will happen if we do a random walk step many times. What is the distribution of the vertices that we are at, something like that. So just to let's look at this natural question to motivate today's lecture. So suppose that you are given a cycle of length n. Okay, and let's say you start at some vertex u. And if I do a random walk step, let's say infinitely many steps, keep doing this, what do you think would be the distribution of the vertices that we are at?
Gaussian.
Gaussian.
With respect, mean will be the same where we started.
Actually, not quite. But is there any other guess? Yeah. Oh shit. Yeah. Sorry. Yeah. Yeah. All right. Yeah. Okay. Yeah, it's uniform. Basically, but Gaussian is a good intuition because in the beginning, your probability will be kind of close to you, right? It's kind of the probability might look like something like you are at U with quite high probability and a lower here. So it's kind of still close to you. But if you do it repeatedly, if you really do random walk step, really for a long time, it will keep the probability mass will keep spreading, and it will converge to uniform. And that's our intuition, and it will be correct intuition. But we will see actually what to prove this formally today. And we can also ask that, okay, we know that it should converge to a uniform distribution, but how fast it is the case that we can say that after this many steps, then the distribution is kind of close to uniform now. That's what we want to understand, and we will see that there are nice applications from this. And actually, we will try to answer this for every graph. How does it what is the distribution after we do a random walk step on any graph? What is the distribution? It's not going to be uniform for every graph, right? Can you give me any example of graph that the distribution shouldn't be uniform?
Star.
Yeah, very good. Star. Yeah. Yeah, because you will likely be at the core here with high probability. Yeah. Yep.
Actually, about proof, I think, can we assume that it will converge and then solve some equations onto this stationary distribution?
Yeah. So, yeah, if we want to prove it, so if you solve the equation, you will get the distribution which is a fixed point. That is, it doesn't change after you do a random walk step. But it might not be the case that if you start from everywhere, from any vertex, it will really converge to the distribution. So you will see like one example very soon.
So there isn't a requirement that there will be a stationary distribution. We cannot say that. Is that right?
Yeah, it's not clear that every graph have a fixed point of the distribution. Like,
You can model them as a Markov chain and just say that it will reduce to zero.
yeah, if we so okay, we are a bit ahead of ourselves. Like we will see soon that one example where the random walk doesn't converge, and we will consider another kind of random walk where it will converge. Yeah. And to talk about things more formally, let's look at. Let me say that a vector pt is just a distribution over vertices after time t. For example, if initially I start at a node u, then p0 is just it's just this vector where it's just everything is 0 except at the index u. Okay, and then we can ask, okay, what is p1? P1 then will be just this thing, right? That is, it's just, so let's say this is U, and here is UCB1. If we do random walk step, then you will get what? You will get like everything 0 except that in the index of in the index corresponding to neighbor of U, each of these will be 1 over degree of U.
It's unweighted.
Sorry?
Unweighted.
Yeah, let's say this is unweighted. Yeah, let's say this is unweighted graph. Yeah, good, thanks. Yeah, and if we say we want to write down pt plus 1 of vertex u in terms of pt, we can write it just by this thing, right? It's just that you just ask, okay, if you are here you ask the probability that you will get at u is just from all of your neighbor v, right? And how much would you would it be the total probability at u is just you summing up over all neighbor of u, which is v, and from v you will go to u with this probability. Okay, and then you condition on the total mass at v at time t. So does this make sense? This probability equation, the equation of this. So note that this is degree of v, not degree of u. Yeah. So it's kind of not symmetric equation. Like the relationship is not symmetric. But and then if we define the matrix to be the matrix to be like W, to be this matrix where A is just an adjacency matrix and D is just the degree matrix inverse, and you inverse here, then you can really verify that from this equation you can write down the vector pt plus 1 as this thing, right? So it's like for each node, V you divide it by degree, and then you like multiply it by A, really. Yeah. Does it make sense? This A is an adjacency matrix. Adjacency. All right. So
D is the diagonal matrix which I don't know.
yeah. D is the degree, diagonal degree matrix. All right. So you see, right? So like if you, let's, should I verify this equality for you? It's fine. Okay. Good. Then you see that once we have this equality, then PT plus 1 is nothing but W to the T plus 1 times P0. Yeah. It's really just applying a matrix several times. Yeah. And now we can ask more formally now, that is, what is PT when T goes to infinity? And how fast PT converges to that limit, right? But let's consider one trivial example where you have one edge. It's just a graph with just one edge, right? And if I start by saying that, okay, this is U and V, and if I said initially I'm at U, so is there a limit for PT? So after one step of random walk, I have no choice but to go to V, and then come back. The next step, I go back to U, and it just like oscillate like this, right? So there's no limit basically. Yeah. And this is actually this oscillation basically happen for every bipartite graph. Because if you have a bipartite graph, no matter what, like you are at, if you start at the vertex at somewhere on the left, then the probability mass on the odd step is going to be on the left, and then on the even step, the whole probability mass is on the right, and back and forth. So there's no limit. So this is the reason basically why we want to look at a similar process, which is not exactly random walk, but it's called lazy random walk. Okay. And this is nothing but, it's just very similar to random walk, but we said that a lazy random walk step is just when you are at vertex U, what you do is that you toss a coin, and with probability half, you just stay put at U. Otherwise, you do a random walk step. Okay, so that's the process. And suppose that now basically we want to talk about lazy random walk, and let's say that PT is now the probability distribution such that, like, probability distribution over V after T step of lazy random walks. And actually, this lazy random walk, you can actually encode it by some metrics as well. So that the PT plus 1 is going to be W tilde times PT. Can you tell me what is this? How does this matrix look like?
A plus d by 2 into d.
A
Plus d by 2 into d.
A plus D over 2 times.
It's just, yeah, we have to put it for the whole.
You mean
Yeah, that is correct.
times the inverse? Right. So this is basically AD inverse over 2 plus I over 2. And this is basically W over 2 plus I over 2. So actually the way I understand it is, the way that I think is easier to understand is this. And yeah, so this is correct. Yeah. But yeah, you can see that from here, it's kind of clear that with probably half you are at the same place. Otherwise, you do a random walk step. Yeah. Okay. Right. So this is our W tilde. And now, if we look at this graph where it's just a trivial graph with one edge, and now we can actually ask what is the limit of PT when which is like W tilde to the T times P0. So what is this in this graph? Yeah, it's going to be 1/2 and 1/2 here. Yeah, this intuition will be correct, and we'll see that. Yeah. So like we will, yeah.
This half actually, is it, why can't it be something else? We only choose with half to be with the same matrix.
So like after enough step of random walk, it will, yeah, right, we're gonna prove this here right now, but like why is this half? Intuitively it should be, right? Because
Not why are you staying at the vertex?
Why are you
already
staying at
half?
the-
Why can't you stay with, let's say, 1/3?
oh, I see. It will be fine. Yeah.
It will be fine.
A 1/2 is just kind of, yeah, arbitrary. Yeah. Any constant should be fine. Yeah. Even like a 1.00, like 0.0001 is fine. Yeah. Yes. Okay. Yeah, thanks. Yeah, that's a good question. Yeah. Okay, so now, so the limit exists for this graph, and now we're gonna show that actually it does exist for every graph. That is actually if you are given a connected undirected graph, and you choose any initial probability, it can be at one vertex or like arbitrary distribution. You know that if you apply a lazy random walk step for like enough time, you're gonna get some vector, which is just the degree vector, divided by like normalized by some constant. Right. So if the graph is a uniform degree, then it means that the distribution will converge to uniform distribution. So it means that it really doesn't matter what is your initial distribution. After like enough many steps, like long enough many steps, you will end up at U with probability which is proportional to degree. So, right. Yeah, and if it is regular, then it's just uniform degree, uniform distribution. So let's prove this, that the limit exists, and it's just a very simple vector, which is degree vector. And now comes again algebra, but yeah, after this this lecture, I think everything is gonna be much more graph algorithmic. But yeah, okay. So I will start by rewriting something. So this is just by definition. PT is just a W theta to the T times P0. And now let me do something which is really nothing. So I just add this like times I here. Okay. And now I look at something different, which is, let's say that I look at it here. Okay. And then this thing will be actually the same thing as like here that you have the power on W. But if I do this whole thing to the power of T, then you can see that it's the same thing as this thing in purple, because this thing and this thing will, when you this thing and this thing will cancel out basically, right? So now we have that PT is d to the 1/2 and something here, but this part is this whole thing to the power of T. And this is nicer because you will see soon. This matrix is a bit nicer to work with. Why is that? Because first note that W theta is not symmetric. It's not symmetric, right? Because note that just W is just this thing. A is symmetric, but you multiply by D inverse on the left, on the right only, so it's not symmetric. But you will see that this thing is symmetric. Why? Because, well, you have that W theta is this. And so if I multiply on the left by D to minus 1/2, and on the right by the D to the 1/2, then basically the second term will be this thing, right? And this is now symmetric. And note that this is nothing but this whole thing is just I minus 1/2 times n, where n is the normalized Laplacian. So let's recall what is n. N is, maybe let me ask, what is Laplacian? So this is n, this is L. L is just D minus A, right? And n is the normalized Laplacian, which is I minus this thing. Okay. And so now you can see that this thing is just changing stuff, and this is just I minus 1/2 times n. Okay. So basically, the thing here is something that we are familiar with. It's like normalized Laplacian, and we have seen it many times. like it is very closely related to how, like the second eigenvalue of normalized Laplacian is like some characterization of expander. So that's why we want to work with normalized Laplacian. And the thing here is just I minus 1/2 n. Okay. So now we understand it a bit more. And now, so note that, like we know about n, but I minus 1/2 n is kind of the same. So first of all, like they have the same eigenvectors, right? And we know that the eigenvalue of normalized Laplacian is between 0 and 2. So the eigenvalue of this guy will be like starting from 1 and like goes down to 0, right? So, and it will be just such that the ith eigenvector here will be just 1 minus this thing. All right. So now let's do one more step. So for now we will have this. Yeah. Let's try to write this thing in such a way that you can, when you multiply it by this matrix, then it's easier to analyze. And to do that, it's just to decompose, to write this in the basis of eigenvector of this matrix, right? So any vector, this is just some vector. And I just write it down in the basis of this eigenvector, of the eigenvector of n, which is the same as eigenvector of this guy. And the coefficient c is just nothing but like how much this vector goes to vi direction. All right. So I just replace this by this thing. Replace this thing by this thing, and I get this. Now now it's good because well, we write down in the basis, like which is the eigen basis. So now when you apply this thing to this matrix, and you apply t times, then it's not just nothing but like you stretch on the ith direction by on the ith direction, like on the ith eigenvector direction, you stretch this vector by this much. All right. Okay. And now now it's looking good now because, okay, for the first direction, we know that this thing, the first eigenvector, first eigenvalue is just 1, because you see, this is just 1. So the first thing is a sum. It's just 1 times c1 times v1, and everything else is just here. I just separate the first term in the sum to this part. Yeah. Okay, so now we like we are in a very good shape. Why is that?
T tends to infinity, this becomes 0.
Very good. Yeah. So because for each of this, for this term here, when I is greater than 1, for I at least 2, this is more than 0. because we know it's good, must be like this is 0 if and only if the graph is not connected, but the graph is connected. So this is not, this is more than 0, which means that this term is strictly less than 1. And when you go, when t goes to infinity, it just vanishes. So pt is just this thing. And now the last thing we just need to compute is just what is C1 and multiply it by V1, this thing. And we verify that it is the degree vector. The point is that this is the only important point, that everything which is on the direction which is orthogonal to V1 just vanished. Okay, so let's just compute this thing. Well, what is the first eigenvector of n? So by now you should kind of remember it by heart, that the first eigenvector of L is all one vector, and the first eigenvector of n, the normalized Laplacian, is like d to the 1/2. And you normalize it by some constant. Okay. So, which means that C1 is just, this is just V1 here, right? It's just an inner product between V1 and this vector. Just recall, right? We write it here. C1 is just like this thing. So now you have this, and now these two things cancel out, right? So you have this thing times P0. And so P0 is just some probability distribution. When you like inner product with all one vector, you get 1. So this is just, yeah, like this, the thing above is just 1 times P0, and this whole thing is just 1. It's just 1. So now you get that this is C1 is nothing but like 1 over square root of this. And now just plug in stuff. This is C1, this is V1, and multiply everything, you get degree vector exactly. So yeah, so this is like, for if you do a lazy random walk, there is a limit for like a unique limit for connected graph. Okay, and we will call this limit a pi. And yeah, the reason behind this name stable or stationary distribution is that, like, yeah, everything, it's not just, yeah, actually the name of this usually means that it's a fixed point. That is, you have this thing, but actually we know that every, like, for every graph, there is a limit too. So the next question we can ask is that, okay, how fast does this expression, how fast does the distribution converge to pi, to stationary distribution, to the limit? Yeah, so very good. It turns out that this will be basically dictated by the second eigenvalue of n. So what I mean, so let's just read this, right? what we will show next is that if you start at any vertex A, and then you look at any vertex B, and you ask, okay, you start at A, and now you look at B, like the distribution, like the probability that you end up at B at time t. You ask how much this probability deviate from what you expect if t is infinity. And the deviation, it turns out, will be something that depends on the degree. That's less important thing, but multiply by this thing. To the t. It's important. The point here is that this is like something which is exponential in t. So what it means here? It means that this thing, second eigenvalue of normalized Laplacian, really dictates how fast PT converges to stable distribution. And moreover, like you see that if the graph is an expander, if it is an expander, which is, it means that this thing is like more than zero, strictly more than zero by some constant. Then basically this thing really like exponentially decrease at every step. So you converge to the stable distribution just exponentially fast in expander. If the graph is not expander, then you just like converge slowly depending on the expansion, basically. Does the message clear about this? Now we're just not gonna prove it. Okay. So I will really just kind of continue from the last proof, really. That is, we wrote before that PT, which is W tilde to the T times P0 is this thing. So just recall this thing, right? Like we write down PT as this expression, and this is nothing but the to write this in eigenbasis, and you just we have this expression basically. I will just continue from here. Okay. So we have that PT is this thing. And we want to ask, okay, how much PT at vertex B deviate from pi? So what is PTB? This is just like a vector, the indicator vector of B times PT. Okay, and we just multiply it on like, and now this thing is just this whole thing times 1B, which is this thing and this thing. Okay. And now we actually see before that this whole thing is just pi, right? So 1b times pi is just pi b. And this thing is just some big stuff that we need to bound. That is because now we can write down this deviation of pt from pi. It's just this stuff. So we need to bound this thing. Yeah. But so forget the hairy expression, but you can see that this kind of depends on, like this whole thing depends on this expression, and this everything here, like each of the term here is at most every term here, each of the term lambda I is at most lambda 2, 1 minus lambda 2 over 2 here. Which, and this term will kind of basically dictate how much this thing go down. So that's the way to think about it. But now we have some algebraic work to do. So, but I will be quick because it's not really insightful from now. So, okay, so we can write Ci. Like I'm just gonna analyze this thing, all right? So Ci is just Bi times this thing, but P0 is just 1A, right? So 1A times this times Vi is just this thing. Okay. And now I'm gonna kind of see what is, so this is just Ci. This is Ci here. And now think of this, when I move this whole thing, maybe I can move this whole thing to here, right? So what I need to analyze is just IB, 1B times this times Vi. But this is again just square root of dB times 1B times Vi. So this whole thing, you can write it down as this thing. So the scalar here become this thing, and this is Ci, and this thing is just this term, like this thing times this. All right. And now, yeah, it's gonna be like just some algebraic step. I will I will just skip. Yeah. The point is that.
So we assume that it starts at vertex A.
Yeah. So now if you want to bound this thing, then it's just you can see that everything here is just like some number, but this number is at most this thing. This is a part where we kind of forget all of the lambda I. We just look at lambda 2. Yeah. Oh, and it's quite important that this is for all I at least 2. Yeah. Now, yeah, just do some algebra. Well, you have that this is sum of this. And you apply Cauchy-Schwarz, you get this thing. And now this is nothing but like, because Vi is just an orthogonal basis. So this is just nothing but the length of 1B and 1A. And the length of 1B and 1A is just simply 1. So this whole thing is just at most this.
It's not basis, right? We don't have I equal to 1.
So, oh, yeah. One
I
sec.
think there will be another inequality.
Yeah. Thanks. Thank you. Yeah. Thanks. Okay. So this term is just this term. And you still cannot forget this scalar. So now we have that, the deviation deviation from stable distribution at vertex B is at most this. Yeah. Okay, good. So now now we can also ask about there is a concept which people call mixing time. Basically, mixing, like we said that a walk after step T is epsilon mix if the deviation at every node B, the deviation from the stable distribution is at most epsilon times pi. Okay. And if you have this in particular, then you actually know that the total variation between pt and pi, which is, this is not exactly the definition, but it is the total variation can be written in this way. It's just summing over all deviation of each event between the two distribution. Basically, this whole thing will be at most epsilon over 2, right? So if the walk is epsilon mixed, the total variation is also small. Yeah, just because this thing is going to be at most a sum b pi b times epsilon, and this over 2, and this thing is 1. So this is epsilon over 2. Yeah. Okay, and now okay. If you look at some random walk process, and in this case we are looking at the lazy random walk. Then the mixing time of a graph G, mixing of G epsilon, is just it's just asks what is the time that you can guarantee that after this many steps, then the total variation is at most epsilon. So you maximize over all possible initial distribution. It can be worse, this initial distribution. And you ask how many steps you can guarantee that the total variation is small. So that's the mixing time. And now from what we have, it's like a kind of a nice thing to kind of know, right? That is okay. You just guarantee that no matter where you start, if you do this many random walk, then you're kind of uniform now, or like a close to degree vector. The distribution is close to degree vector. It turns out that mixing time is just basically 1 over second second eigenvalue of the normalized Laplacian. So we have seen normalized Laplacian and its second eigenvalue. And you know, we have seen that, okay, this lambda 2 thing is kind of, by Shiger inequality, it characterizes whether the graph is an expander or not. But sometimes it's not easy to think about, right? It's just some algebraic stuff. It turns out that mixing time is just another way to think about it. How? Here. So mixing time is basically 1 over lambda 2. And maybe this is like, think of this as log n factor, basically. Log n. So mixing time is bounded above and below by 1 over lambda 2. And there is just one log n factor that is a slack. And this is kind of nice because sometimes it's just easier to think about random like about mixing time than second eigenvector. Sometimes it's easier to analyze algebraically second eigenvector, and once you do that, you get mixing time too, right? So now the proof, like we kind of have almost everything to prove this, and I actually will omit the lower bound proof and only show this upper bound. Okay. To show the upper bound, it means that we need to say that, okay, no matter what the starting distribution is, after this many steps, you mix. And actually, it's not hard to say that the worst distribution that it takes longest to mix is always like you start at one single vertex. Because otherwise, like if you start from other like distribution, the endpoint is just a convex combination of the walk that you start from one single vertex, and you can take the worst vertex that takes the longest. You can think about this more, but yeah, you can just really look at one starting point at one vertex. And we have seen that if you start at vertex A, the deviation at B is at most this. And now just calculate. Okay, what it means by we want to say that this thing should be at most epsilon pi of B. We want to ask for the smallest t that you can guarantee this thing, right? And pi of B is nothing but dB over dV. So I just ask for the smallest t such that this thing holds. And you just do some algebra. You move this to the right, you get this thing, and now you have this part. But you can use that 1 minus x is basically e to the minus x. It's a kind of very close approximation. So I can replace this part by e to this thing. And now take the log on both sides and do some change thing on the, and you get this part. So basically, whenever t is bigger than this thing, then you can guarantee that the walk is epsilon mixed. which means that the T mix is bounded by this. Because, yeah, you have this term, and this term is just in the log, and this is like, this is no worse than D min. Yeah. Okay. So doesn't matter much about the calculation. The point is really that, yeah, mixing time is just 1 over lambda 2. That's a point that we need to have in mind.
So when we start at the high degree vectors, then it takes longer time to mix it.
If we take at a high degree vertex, I guess so. I'm not sure actually.
Or it other way maybe.
I honestly don't know. Yeah, we can think about this later. Yeah, I'm not
By
sure.
the same convexity argument, the best possible distribution is also starting from a single point, right?
Yeah.
Okay.
So that single point, it's not same for any vertex, right?
It's not.
Maybe for one vertex, like either with highest degree or lowest degree.
Yeah. So I don't think that it depends only on degree. Like it should depends on the structure of the graph. Like for example, if let's say that
If it's in a more connected part and
yeah,
versus less connected part with the same degree.
yeah, I think I think it should depend on the structure of the graph. The degree might not really like determine if it's the best or the worst. Yeah. Okay. So now we have everything that we need from that to answer the question from the beginning of the class. We see that okay, if you do a random walk step in cycle many times, then it converges to pi. But for pi in cycle, it's just all like it's just all one vectors. And how fast does it converge? Well, I didn't prove this, but actually when G is cycle, this is 1 over n squared. So it means that you will need maybe something like so T mix, tau mix is going to be at most n squared log n, something like that. Yeah, and actually when it is not clear if what is this or this, knowing one implies another. Basically, on expander, you know that lambda is big, so mixing time is going to be polylog if lambda is at least 1 over polylog. And on the path, actually,
So just one is less than cycle.
yeah, it's just like very similar to cycle. And actually there is a good reason why mixing time should be at least n squared, because like in random walk, if you let's say you start at like, let's write it like this is at 0 and this is like n minus. If you do random walk at 0 and you do it for t step, so well, if you do it for t step, then like with high probability you will be somewhere at like square root t. So you will not ever like go beyond that. this is just from, I'm not sure if Nikhil teach this in his lecture, but basically you do random walk for T step. Yeah, you are like between like minus root T and root T. So if you don't even go beyond that. So if the path is like of length n, you should take something like at least n square, just even to reach the endpoint. Yeah. But T mix is gonna be like something like n square. So lambda 2 is gonna be something like 1 over n square. How about like dumbbell graph? Something like this. So this is a clique. This is a clique, and it's connected by one edge. You can see like just by intuition that T mix should be n square too, because like, or at least n square, at least n square, and the reason is that like, if you are at any node, it takes like a probability 1 over n to just go to this guy, and you need to be correct again. That is, this node need to kind of go here instead of n choices here. You need another like a 1 over n like event to happen. So just to cross the path, this happen with probably 1 over n square. So T mix should be at least 1 over n square. T mix should be at least 1 over n. And just by knowing this, you can bound the second eigenvector value too. And there is like actually even worse than dumbbell graph, which is something like, it's called Bolas graph. And this thing is a weapon. Like, it's like a weapon where you have like some chain here, and this is like some heavy stuff. But anyway, so it's just a graph where you have a clique here and an n clique here again, and in the middle is like a path. And now, yeah, you can see too that like, if you are at a node here, it will need like, you take actually like n cube step just to reach other side. You can think about this, but then lambda 2 of this graph is going to be 1 over n cube. So exercise. Yeah, I forget how to write it. X. Yeah. Yeah. So, but actually, there's some nice thing to know. Like, that is, this graph is actually like, among all unweighted graph, is the one that is hardest to mix already. So you actually show in the homework that if the graph is unweighted, then lambda 2 is going to be at least 1 over n cube. So you're not going to be too small. Like in weighted graph, it can be small, very, very small, right? Because like the graph can be like this graph where this is like infinite and this is like epsilon. So you're gonna just walk between this guy and you don't ever go to this. But in unweighted graph, you can get some at least polynomial bound on the lambda 2, which means that for any graph which is unweighted, the mixing time is going to be at most n cube.
So there are some sometimes in literature where we say weights are bounded in that.
Mm-hmm.
In that case.
In that case, you will get some polynomial bound here too. Yeah, if the weight is bounded by polynomial. Yeah. Okay. So now I'm gonna go quickly to the application of random walk. So first, if you have an unweighted graph and you have node S and T, and if I want to find a kind of short path between them, but I want to do it by not even reading the whole graph in sublinear time, then there is like a cute algorithm to do this, given that we know how to do random walk. So imagine this. Suppose that I do a bunch of random walk from S. I do enough times such that I end up with like a random guy. Like I do a random, so let's say that I do a random walk step from S, T, like T mix step. So let's say I end up at V1. So this guy, V1, is gonna be random nodes, right? Like at least according to its degree, yeah. So, and okay, forget this. And let's say I do this for like root n many times. I repeat this. I do it again, I get V2, do it again and again, and just repeat this for square root n many times. And let me call this set S. It's just all the vertices that that I end up with from S. There are square root n many guys in S. And now I do the same process from T. So maybe U1, U2, U3, and call this T. And if S and T are not disjoint, then you can see that we can just extract a short path from it, right? We can get a ST path of length something like 2 times a mixing time. And the total time to do this whole algorithm is just square root n times mixing time. So in expander, what does it mean? So before that, actually, it will be the case that S and T gonna be like intersecting with high probability. And the reason is just kind of just birthday paradox, basically. Basically, so if you recall birthday paradox, if you have n bins, like n bins from 1 to n, and if you throw like something like square root n balls to this bin randomly, then at least 2 balls gonna be land on the same bin, right? And here you can think about it, or I explain more in the exercise question, but it's kind of the same. And by the way, this thing, the number of balls here, when I throw the balls, it's just according to some distribution. It doesn't need to be uniform distribution. If the distribution is more skewed, that is not uniform, actually it's gonna be better. It's gonna be easier so that you collide. So now you see, right, that S and T should intersect by the same reasoning here, because S is just like you throw like a root n balls into into n many vertices. You choose square root n random guy according to some distribution. T is also the same. So one pair gonna collide at some node. And it means that if the graph is expander, then this algorithm, what does it give you? It gives you a path which is just log n length, very short path, but in time which is just square root n. So sublinear time. So this is quite a cool algorithm actually. Question? All right. Are you with me actually? Is this okay? Okay. Next application is connectivity in very small number of space, small space. You just use log n bits of space. The goal is that you are given a graph, and S and T, and two nodes, S and T, you want to check if S is connected to T. And you can assume that the graph is unweighted too because you care about connectivity. It's not about length. And the setting is that, let's say that this graph, let's say you have adjacency list, but it's read only. You only have like small number of bits for a working space. By working space, I mean the place where you can read and write. This you have only like log n bits. Okay, and we wanna check if S is connected to T using just log n bits where you can write and read. But you can read the thing in graph, but you cannot write thing on top of this. And now the algorithm gonna be very simple. Just start from S, and you do a random walk for this many step, and enter the fifth. And if you visit T, you return yes. And indeed, if you visit T, then S is connected to T, right? And otherwise, if you never visit T, then you just return no. So clearly, if S is not connected to T, then the algorithm will never return yes. You always get a no. But we want to say that if they are actually in the same connected component, then with high probability, you actually will visit T. And know that why the space of this algorithm is just log n. Because the only thing that we, sorry?
Just one vertex value.
Yeah, right. You just need to know where are you right now, and you just need to remember the number of steps you have so far. So the number of steps is never more than into the fifth, and so that is one number, which is log n bits. And the name of the vertex is just log n bits again, because there are just n at most vertices. Yeah, so we'll.
This is only for expander?
No, this is for any graph. You can check connectivity in log n bit for any graph, but the time is quite slow. And why is this the case? Well, suppose that C is the connected component that contains S and T. So we know, I claim, and you show in the homework, that for any unweighted connected graph, the mixing time is at most n cube. And which means that if you perform T mix many steps of random walk, you will visit t with probability something like degree, like proportion to degree of t, which is degree of t over the volume of c. But this is always like at least 1 over n squared, right? Because the degree of t is at least 1, the volume of the whole component is at most like n squared. So with like some small probability, you will visit. But if you repeat like enough time, then you will visit with high probability. So you just perform t-mix step of random walk for n squared times log n many times. And that is like n cubed, n to the 5th. You will visit like the probability that you never visit t is very small. Yeah, it's very interesting if you can improve the time to something like, instead of n to the 5th to something like n squared, to something reasonable. But still use like small space. I think this is very interesting question. Yeah. Like it's open. So the last thing I want to tell you is just an algorithm to sample a spanning tree. So this is like, the problem here is just you have a connected graph. So there exists a spanning tree because the graph is connected. And if you want just some spanning tree, it's very easy. Just breadth first search or something. Now the question is, if you want us to sample like almost uniformly a random spanning tree, how to do that? Here I will just give you just actually so actually let me just tell you this. So this is just a very natural problem, and there are like a lot of the series of papers that try to do this, like from 20 years or something ago. People can do like in polynomial time and improve it to mn and improve it to m root n and so on. And then like maybe last 2 years or 3 years ago, there was a paper that said that, okay, you can do it in this time. And the paper is like 200 pages. And then just recently, last year, there is a proof that says that this time is enough. And the algorithm is super simple. And I will just tell you how to do that on Thursday. But I will not prove it to you. But like this is just a way to tell you that like the fact that you can mix very fast on expander is useful in a very different way than how I just told you before. And it's gonna be the core idea behind this thing, but I will just sketch the idea to you. And basically, we have seen like a 5 way to view expander in a very different way. And let me just try to recap all of this on Thursday. And after that, we will, on Thursday, I will just recap this briefly. And then we will now go to some algorithmic part of the course, which is going to be fun. Okay. So that's it for today.